Comes on everyone. Let's start off. Perfect. So last thing that we did, waves on a string. Hope everyone has started doing it. I did send you a sheet. Hope you had a look at it. What is this? Great. So we will be starting off with sound waves today. Now, if you remember the whole definition, right, how we started, a wave is nothing but propagation of a disturbance. And what is a disturbance? Disturbance is nothing but the change in property with respect to surroundings. And what is a property? Any quantity, displacement, pressure, electric field, magnetic field, density, anything that you can think of that's changing. So when you study sound waves, the property that is changing is your pressure and density. So when sound waves propagate in a medium, the property that changes are change in pressure and density and displacement. So if you want to study a sound wave, you can study actually any one of them. It is preferable, right? We prefer to study in terms of pressure because we humans, right, we are sensitive to pressure. We our ears don't understand what is displacement; they understand what is pressure difference. So it's preferable to study in terms of change in pressure. Since humans and instruments detect pressure. So here the important word is this: the change in pressure. It is not pressure. What we study is change in pressure. I'll tell you what it means. Think of like this. So just to give an example, so when we write the equation y is equal to a sine kx plus or minus omega t plus phi. If you remember, this y was not y coordinate. This y was property, some property that is changing. For waves on a string, y became the y coordinate of the displacement. So for sound waves, the equation will look like this. Delta p is equal to delta p max sine kx plus or minus omega t. So when you're studying sound wave, we prefer to study in terms of change in pressure. This is change in pressure. Delta p max is your pressure amplitude. So henceforth, right, we will say displacement amplitude and pressure amplitude. So we will use that word pressure amplitude, displacement amplitude, because if I just say amplitude, I don't know whether you're talking about displacement or pressure. So pressure amplitude is the maximum change in pressure. Getting it? So the thing is, when you studied waves on a string, you studied displacement of the particles. When you're studying sound waves, you're studying pressure at a point, the change in pressure at a point. Meaning, think of like this. I'll give you an example. Let's say if there is no sound in the region, if there is no sound, the molecules are equally spaced. And everywhere the pressure is P naught. So pressure is P naught, P naught, P naught, which is 10 power 5 pascals. Now, when a sound is passing through this region, now remember this is a longitudinal wave. That means the particles are going in the direction of the wave. So they're also going left and right. So at some places, the molecules will come closer. Some places, molecules will expand. Some places, again, they'll get closer. Again, they will expand. So you get compressions in rare fractions. So here the pressure will become P naught plus delta P max. This is your compression. Here it will become a rare fraction. This will be P naught minus delta P max. So pressure will decrease here. This is a rare fraction. And so on. So if you look at this delta P value, right? Delta P max is around 20 to 40 pascals. So delta P can be positive or negative. But pressure is always positive. So what you're detecting is this delta P actually. See, I'll tell you what is happening. If you look at your eardrum, let's say if your ear inside, right? We have an eardrum inside. If there is no sound anywhere, the pressure inside the eardrum is P naught. Let's say this is the inside part of your ear. This is the outside. Outside also pressure will be P naught. So your eardrum will be flat. Now when a compression comes and hits the eardrum, the pressure inside is still P naught. Outside will be P naught plus delta P max or whatever delta P. Your eardrum will actually stretch like this. It's going in. And then when you get a rare fraction, P naught minus delta P max, your eardrum is actually becoming like this. So your eardrum is continuously stretching in and out. So right now when I'm speaking, the sound which you're hearing is nothing but your eardrum oscillating front and back, and it generates voltage signals. And that voltage signals is what your brain is thinking is sound. So what your ear is measuring is not pressure. Your ear does not know what is pressure. It will think both are balanced. What it is measuring is this difference of delta P max. Is that making sense? If the pressure inside is P naught and outside is P naught, your ear will think everything is normal. It cannot tell the difference that there is a pressure. It will notice a difference when there is a P naught plus delta P max and P naught minus delta P max. So what you're studying is not pressure, but change in pressure. Is that statement making sense? So that was a CET question in the exam. While studying sound waves, which are the property we are studying? Pressure or change in pressure? It's not pressure that you're studying. You're studying change in pressure. This is what is happening to your eardrum. So when you say 100 hertz frequency, it means your eardrum is oscillating 100 times to and fro. That is what is frequency. How fast is your eardrum vibrating? Any doubts so far? So far the story is this. When a sound wave is moving in a medium, air, water, or anything, the particles are oscillating to and fro. Some places they'll get compressed, some places they get expanded. So the pressure will become P naught plus delta P or minus delta P. So the delta P can be positive or negative. Pressure can increase or decrease. The change in pressure. And this value is not really big. Look at this. This is 1 lakh and this is 2030. Means you're looking at 1 lakh plus or minus some 30 ka difference. So this is not really a very big value. So your ears actually measure such a small change in pressure. And that's what you think is sound. Everyone clear with this so far? So what we are studying is change in pressure. Now, how do we get a relation between displacement and pressure? So consider a region with bulk modulus B. Hope you remember the formula for bulk modulus. Bulk modulus is equal to minus dp by dv by v. Comes from elasticity. Now consider a region whose particles are x and x plus dx. So there are two particles here at x and x plus dx. So let displacement of the particles at x be y. That means this particle, which is at x, let it go forward by y. And the displacement of the particle at x plus delta x be y plus delta y. So if you go little forward, the new x coordinate will be x plus delta x, and let this particle go y plus dy. Let the area of cross section be S. From here we get volume of this region V will be area of cross section into thickness dx. The change in volume dV will be the cross sectional area into the change in displacement, which is s dy. Because see, if the guy behind you is going y and the guy in front of you is going y plus dy, then the difference in displacement is dy. Now if I substitute this in the formula of bulk modulus, minus dp by dv, which is s dy. The derivation is not that important. The final result is important. We get dp is equal to minus bulk modulus dou y by dou x. This is the relation between pressure and displacement. Very important formula, should definitely mark up. So we took a small region. So this is what happened to the region. This moved y and this moved y plus dy. So the blue one became this red one. So it has expanded by dy. So the change in volume is s dy. The initial volume was s dx. I just substituted this in the bulk modulus ka formula. And this gave you a relation between pressure and dy. Dy is your displacement. So let me just put down this again. So this is an important formula there. So dp is equal to minus bulk modulus dou y by dou x. This gives you a relation between displacement and change in pressure. Means if you tell me how the particles are moving, I can find the pressure with this. So look at the formula. So what was the regular formula if you remember? Y is equal to a sine kx minus omega t. Your standard progressive wave. What is this y? Displacement of particles. Now be careful here. This y is not y coordinate. This is the displacement of particles along x. That means if you look at this, so these particles are moving this way, inward. These particles are going outward, right? And so if you see, this is y here. So particles are going to and fro. And the wave is also going forward. Think of like this. You're standing in a queue and someone pushes you from the back. So people are going front and back and the disturbance is also going in the front. I hope you remember longitudinal wave. The particles go in the direction of the wave. I showed you that slinky guy example. There. So the particles are moving in the direction of the wave, longitudinal wave. Now, if I use this relation and if I do dou y by dou x, that would become ak cos kx minus omega t. If I substitute there in the formula, I get dp is equal to minus bulk modulus dou y by dou x will be bak cos kx minus omega t. I can rearrange this. We get dp is equal to bak. I can send the minus sign inside. Then this will become sine kx minus omega t minus 90. Sine 90 minus theta is minus sine theta. This is your relation. And if you look at this formula, BAK, this is your delta P max. Meaning in a region, this is the maximum change in pressure. This is your second important formula there. Results are more important than the derivation. So let me put down all the important formulas. The first thing, the maximum change in pressure is given by bulk modulus, amplitude, K. Means if the particle is going 1 mm, another particle is going 2 mm, the 2 mm particle will generate double the change in pressure. B is your bulk modulus. That means if you're sending sound in water or sending sound in a metal, metal has more bulk modulus. So the change in pressure is more. In that, we don't call it pressure, but yeah, the compression is more. The stress we say in metals. This is a displacement amplitude. You guys should write down these formulas. These are the three main things. This is a more theoretical question. The displacement, if you see, this was the displacement. This was the pressure. Displacement and change in pressure are out of phase by 90 degrees. That's a good theoretical question. That means when the displacement is at the extreme maximum, the change in pressure is zero. When the displacement is zero, the change in pressure is maximum. So the both are out of phase by 90 degrees. K is 2 pi by lambda. There. So these two formulas, delta P max and displacement. These are the four important things. So this equation gives you the relation between pressure and displacement. So if the particles are going to and fro by 1 or 2 mm, how does that affect the pressure? We never had a problem like this in waves on a string because there we studied only displacement. The problem here is the sound waves, right? Can be studied in three different ways: density, pressure, and everything. So suddenly it becomes a mix. We are so used to studying in displacement. We are converting that into pressure now. All clear with this? Let's see a few questions. That is the best way to get the hang of it. So if you see, there are a bunch of formulas which you need to know. This is a YX graph of a longitudinal wave. Be very careful. If they say YX graph of a transverse wave and YX graph of a longitudinal wave, they're very different. Because in a longitudinal wave, if this is your x-axis, if this is the mean position, the particles are going in this direction to and fro. So this is y. Y is not the y coordinate. Y is the displacement of the particle from its mean position. And y is also in the direction of x. And if I have to give an example, think of like this. So let's say this is your x-axis. Let's say we have a particle here at x is equal to 2 meters. This particle is going on this side and this side, let's say 3 millimeters, and it is going this way minus 3 millimeters. Meaning the particle at 2 meters can travel 3 millimeters front or 3 millimeters back. So this is your displacement amplitude. this is not going up and down. So this is y value. So y ka value is this. So the how to read this is this: the particle at x is equal to 2 meter oscillates with an amplitude of 3 mm along x-axis. That is the meaning of y. Y is not the y coordinate. I hope that example was clear. That is a mistake people do. In case of a transverse wave, you're lucky. Basically, the graph and the string both look identical, not in a longitudinal wave. So now if someone gives you a graph, and if I give you 4 points now, A, B, C, and D, which points have maximum pressure? Let me ask you one more thing. People get confused between these two questions again. Which points have maximum change in pressure? They're completely two different questions. Just adding that word change changes the whole question. Let's give it a try. So what I gave you is a displacement graph, but I'm asking you for pressure. And the only relation you have is this guy. dP is minus bulk modulus dou by dou x. That formula is very important. You know, that formula is like this guy. V particle is equal to minus V wave dou by dou x. Yaad hai? So here it is dP is equal to what do you call it? Bulk modulus into dou by dou x. So these two are important ones. Most people don't remember them. Take a minute or two. Let's see how will you do this. It's a good one. A and C, B and D, and A and C. Okay. I'll show you two ways. Okay. First, I'll show you purely mathematical. Then we can use little logic also and figure it out. Let's see. People did get some answers. Okay. Let's see the first part. But the main thing I want you to understand what is y here. Y is not up and down. So that's the main thing. First, let's do brute force mathematically. There's nothing much to think mathematically, and I feel mathematically is more safe. So dP is minus bulk modulus dou y by dou x. So this is indirectly minus bulk modulus into slope. Remember, dP is the change in pressure. So we can clearly see slope at A is positive. At point B, slope is 0. At point C, slope is negative. At point D, slope is 0. That means if you look at the pressure dPA, this would be minus B into this is the maximum slope. And that is also positive. That means this is minus delta P max. So that means at point A, the change in pressure is maximum. So that means what is the pressure at A? Pressure at A is P naught. minus delta P max. So basically PMA, there is a rare fraction. So pressure at A is actually less than P naught. If you look at dPb, slope is zero, so pressure is zero. That means pressure at B is equal to P naught only. If you see dPc, this will be minus B into negative maximum slope. That means this is a plus delta P max. So understand this thing. So at A and C, the change in pressure is maximum, but one is a positive maximum, one is a negative maximum. That's the difference between them. So the pressure at C is actually P naught plus delta P max. Similarly, pressure at D, dPd is also zero. Therefore, pressure at D is also P naught. And now coming back to the question, look at the first question. Which points have maximum change in pressure? Which points have maximum change in pressure? A and C. So that is the maximum change. Which points have, which points are maximum pressure? Sorry, which points are maximum pressure? PD, PC is greater than PB, is greater than equal to PD, is greater than PA. That is the pressure co-order. PC is the maximum pressure. Which points are maximum change in pressure? PC and PA. Are you getting the difference between both the questions? If I simply say maximum pressure, means what is the actual value? Maximum change in pressure, what is the change in value? So A and C have a maximum change in value, minus delta P max and plus delta P max. But one is a positive change, one is a negative change. So that's your minimum and this is your maximum. Is everyone clear with the difference there? So there are two different questions. If they ask you find the maximum pressure, so you have to be careful. Or if they ask you pressure, it is something else. Don't mix up both of them. What is another way to do this? Listen to this thing alternatively. By chance, you forgot the formula and you don't realize it. Look at the point here, okay? Look at the point A here. So look at the particle in front of A. If you look at the particle in front of A, this thing is a positive displacement, plus Y. If you look at the particle behind A, that is a minus Y. What is the meaning of this? This particle here is at the mean position, but the particle in front of you is going ahead. The particle behind you is going backward. Are you getting the meaning of it? If you look at the particle in front of this point A, the particles in the front are going ahead. The particles behind are going backward. If you look at the particles at C, look at one point in the front and one point at the back. The particles in the front have negative displacement. The particles in the back have positive displacement. That means here the particles are coming towards C and they're coming towards this way. This is a compression. This is a rare fraction. We can clearly see PC is greater than PA. Is that making sense logically? Look at the particles in the front, look at the particles behind. If the particles in the front are going away from you and the particles behind are going away from you, that means in that region, the whole gas is expanding. It's a rare fraction. If the particles are coming towards you from both the sides, meaning the gas is getting compressed. That's a compression. So no equation, nothing. You can see the picture and try to understand. So in this, observe the particles in front and behind the point. So Y here is a displacement in the direction of X. This is more intuitive with the graph without any marks. All clear with this? Next thing. The speed of a sound wave is given by 330 meters per second. all the formulas you studied in waves on a string are valid. Frequency and all that stuff. Frequency is 165 hertz. Amplitude is 2 into 10 power minus 6 meters. It is given in meters. So it is displacement amplitude. Difference between maximum and minimum pressure in a region is 20 pascals. So there I'm giving you all the information. Using this information, find the bulk modulus. Now, all the formulas that I taught you, you have to use them and figure it out. Let's see what will you do. What are the formulas? First thing, the difference between maximum and minimum pressure. The word, right? Be careful with that. So what is the maximum pressure? P naught plus delta P max. This is the maximum pressure. He didn't say delta P max. Minus minimum pressure. He didn't say the difference between maximum change in pressure. P naught minus delta P max. So the maximum pressure in a region is P naught plus delta P max. Minimum pressure region is P naught minus delta P max. And he's saying the difference between these two is 20 pascals. So from here we get delta P max is actually 10 pascals. And we know delta P max is nothing but BAK. A ka value is given. B ka value we need to find. K ka value I can find. And we know speed of sound is equal to frequency into wavelength. So from here we get wavelength is equal to 330 by 165. That is 2 meters. So from here we get K ka value, which is 2 pi by lambda, which is pi. Substitute here everything. We get 10 bulk modulus 2 into 10 power minus 6 into pi. Simplify this, you'll get bulk modulus ka value. You get 10 power 7 by 2 pi. Yeah, right, Param. Is this clear, everyone? So there, you should know your bunch of formulas. Delta P max is BAK, C is F lambda, all those stuff. And this word is a trap. He didn't say the maximum change in pressure is 20 pascals. He said the difference between the maximum and minimum pressure. You can add a few more words there in a region. Yes, 20 pascals. All clear with this? Aditi, clear? Amrita, Pratyasha, Srihari, Samyak, Shreyansh, clear? Next thing, speed of a longitudinal wave. Now, for this, the derivation is not important. This is given by, remember, sound wave is a longitudinal wave. Every longitudinal wave is not a sound wave. The velocity of a longitudinal wave is given by root over bulk modulus by rho. So these are waves in a fluid, sound waves, all these things. So when you take a rod and hit with a hammer, the disturbance travels. If you're talking V longitudinal for thin rods, now for thin rods, see, bulk modulus is defined for volume. When you're speaking, you're sending the sound in three-dimensional. But for rods, it is a thin rod, so Young's modulus by rho. The formula changes there. So B is the bulk modulus. In case you forgot what is this bulk modulus, you should refer elasticity, take notes. Y is your Young's modulus. Rho is your volume density. Not mu. Mu was linear density. There. Because thin rods don't have volume, bulk modulus doesn't make sense. Now using this, consider we have a rod. What you did, you took a hammer and you hit the rod like this. You're hitting it from the bottom. Then what would happen? This rod would become like this. You get a bump. I am exaggerating the figure, but you get a bump like this. So the bump is going forward. This is your V wave. And this bump is traveling up and down. So this is a transverse wave. So if we hit the rod like this, the wave generated is a transverse wave. And V transverse will be root over T by mu. Yeah, that's exactly for a string, but we can approximately use the formula there. The same rod, if you take the hammer and if you hit it this way, you're hitting it along the rod. Now the rod, right, will actually get a bulge like this. And this bulge is traveling forward. Here, the particles are oscillating left and right, and this is a longitudinal wave. Meaning, depending on how you're hitting the rod, you can generate a longitudinal wave. And here, V longitudinal is given by root over Young's modulus by rho. And now, if you try to take a ratio, V longitudinal, this will be root over T by mu by Young's modulus by rho. If you remember the formulas, Young's modulus is equal to tension length by A delta L. So from here, I get T by Y is equal to A delta L by L. And we also know rho is equal to mu by area. So rho by mu is 1 by A. So substitute everything here. T by Y will be A delta L by L, and this is 1 by area. You end up with root over delta L by L. And if you remember, delta L by L is nothing but strain. Stress and strain, hope you remember. This is the relation between longitudinal and transverse wave. Means on a same material, if you generate both the waves, they don't have same speed. They travel with different speed. Ever heard about this thing, S waves and P waves in an earthquake? So normally whenever an earthquake is generated, right, they generate two types of waves. So this is what actually happens during an earthquake. So let's say this is the earth core surface and they use the word something called epicenter. So epicenter is the point, where the earthquake has started. So that is where the disturbance has started. So from here, what will happen? You will get a one type of a wave. So basically, it is being pushed up and down. It is also going left and right. So one type of a wave is traveling this way. So basically, in this case, the particles are oscillating front and back. Right. So these are your longitudinal waves. The P waves are your compressional waves, or they can also call it primary waves. So these are like, longitudinal waves. You can think of like, pressure waves or something like that. So longitudinal waves or compressional waves. So they have different names like this. The second type of waves, the earth, right? It is pushing, the wave is going forward, but the whole thing is getting compressed like this. So these are called S waves or shear waves. So shearing stress. These are transverse waves. So when you get an earthquake, we get two different types of waves. And if you see, the P waves will reach the ground first. You can clearly see the formula. Strain is always less than 1. So V longitudinal is greater than V transverse. So even before the things reach here, meaning this is what will happen. So if you're standing there and if you got an earthquake right now, your body will go up and down first. After few seconds, then your body will go left and right, and then you'll fall down. So first you'll get an up and down ka motion, then you get a left and right ka motion. So there's a small difference in time interval between both the waves. Using this, you can actually locate where the earthquake has started. Recently read, I think last month or something, there was a big earthquake in Venezuela. I don't know if you have read the news. And then what happened, right? All the Google phones, right? All the phones which had Google Maps and everything, they started sending an alert to everyone. There's an earthquake. Something like not very big time, but I think 10, 15 seconds before, they all got a signal. And the simple thing was what happened? All the phones got GPS, right? They started observing P waves. So once they got the P waves, the GPS understood was earthquake is coming, and S waves are actually more dangerous because see, if you're having a building, right, with the pillars and everything, if you push the building up and down, there's no problem. The building will simply, the pillars will support it. The problem comes if you try to shake the building left and right, then the building will tilt and will collapse. The problem is that left and right waves, the up and down waves are kind of safe actually. So people had some 10, 12 seconds of time interval, right? Before they realize these S waves are coming. Not much, but 10, 12 seconds, right? Someone can get out of the house, someone can get out of the door. It benefits a bit. So the Google ka GPS, right? It figured out earthquake is coming and it simply started sending alerts on its own to every phone. Boss, there's an earthquake, run away. Karke. So yeah, this is how they do. And this is how they actually study the earth ka core. Ever studied 100 kilometers below the earth, something is there. Who has dug a hole till that depth? So what people do is actually they send both the kind of waves and they study the difference in time interval. And from there, they get the bulk modulus, density, and all that stuff they study. So this is the techniques you study to study mineral reserves, oil reserves, and all that stuff in the ground. It's also called as, I think, seismology or something like that. So seismography, seismology. Yeah, this could be a good advanced paragraph question. S waves and P waves, they can make a small paragraph out of it and they can frame a question. Clear with this? That's one thing about longitudinal. Next thing, when you talk about the sound wave, the first guy who wanted to study the sound wave, as usual, is Newton. So we call it Newton's speed of sound. This guy has no work. He's there everywhere. Yeah, sometimes I feel he might be a time traveler. Like he must have got some H.C. Verma or something, must have taken the book and gone back and started writing every theory from there. Could be. So this is what Newton thought, when Newton said, okay, sound is propagating in atmosphere and temperature of atmosphere is constant. So he said that means the temperature is not changing. This is what he felt. Not a bad logic though, but since sound propagates in atmosphere and the temperature of the atmosphere is constant, right? He assumed propagation of sound is an isothermal process. Now, for an isothermal process, PV is equal to constant. Differentiate on both sides. This will be PdV plus VdP is equal to 0. If you arrange the terms, you get bulk modulus is equal to minus dP by dV by V, which comes equal to P. You have done this in elasticity. That means for an isothermal process, the bulk modulus of a gas, right, is the pressure only. So the pressure of the gas is the bulk modulus. Now coming back to the formula for the longitudinal wave, V sound is nothing but root over bulk modulus by rho. When you substitute here, we get V is equal to P by rho. And from ideal gas equation, we know PV is equal to nRT. We can write this thing as P is equal to N is mass by molecular weight. RT. So mass by volume becomes density. So we get pressure by density is RT by molecular weight. So this formula can be written as root over R into temperature by molecular weight. R is the gas constant, T is the temperature. When they actually calculated this value, the number, right, came to be around 280 meters per second, which was wrong. The experimental value of sound was 330. So Newton understood was something was wrong here. They couldn't figure out what, but they realized there's something wrong with the whole thing. Then there is a guy called Laplace. He comes and says, yeah, sound is traveling in vacuum, I agree. But the problem is the sound compressions and rare fractions. Understand, when you say frequency is 100 hertz, that means the gas is compressing and expanding 100 times per second. Means the compression and expansion happens in 1/100th of a second. So since gas compresses and expands so fast, you're not giving enough time for heat exchange. If you're compressing and expanding in 1/100th of a second, you're not giving enough time. So since the gas compresses and expands rapidly, there's no heat exchange. This is an adiabatic process. That is the meaning of 100 hertz. The gas compresses and expands 100 times per second. So then we write the equation PV per gamma is constant. I hope you remember what is gamma, adiabatic constant. Now when you differentiate this on both the sides, we get dP V power gamma plus P into gamma V power gamma minus 1 dV is equal to 0. If you arrange the terms, we get bulk modulus is minus dP by dV by V comes out to be gamma P. Now if you apply this formula, V sound is root over bulk modulus by rho. Bulk modulus is gamma P by rho, and P by rho is gamma RT by M. This actually comes out to be 330. Pretty close to 330. This was right. So that's our formula for velocity of sound in gases. In solids, we have to use that bulk modulus. Root over gamma RT by molecular weight. Be careful, molecular weight must be in kgs. There, that's your new formula, everyone. What is our gas constant? 8.314. You can just use 8.3 joule mole per Kelvin. T is temperature in Kelvin. Gamma is given by 1 plus 2 by F. F is the degrees of freedom. Hope you remember, this comes from thermodynamics. Monatomic is 3, diatomic is 5, diatomic at high temperature is 6, and so on. In case you forgot, we have a full table for that. You should I think we wrote that in KTG. Here, this is the full table there. Page 117, thermal expansion. Monatomic, diatomic, triatomic, nonlinear, diatomic with one vibration mode. This is the gamma ka value, CP, CP, and everything. So this is where we had the discussion, degrees of freedom. Page 113, thermal expansion. Now, a few things here. If sound is propagating in a mixture of gases, so they will say 2 moles of helium and 1 mole of hydrogen. Then the formula will become V sound will be root over gamma average R temperature by molecular weight average. How do you get gamma average? Gamma average is 1 plus 2 by F average. Be careful. You should not take N1 gamma 1 N2 gamma 2. Gamma is not a linear function. What is F average? N1 F1 plus N2 F2 by N1 plus N2. What is molecular weight average? N1 M1 plus N2 M2 by N1 plus N2. So example, if someone gives you 2 moles of helium and 3 moles of hydrogen. F average will be helium is monatomic, so 3, hydrogen is diatomic 5 by 2 plus 3. M average will be 2, helium is 4, hydrogen is 2 by 2 plus 3. And this is in grams, so into 10 power minus 3 kg per mole. Then you substitute the appropriate formulas and finish it off. All clear with this? A few more theoretical things. We know V is equal to root over gamma P by rho. Or you can write this thing as gamma RT by M. This is one of the most common theoretical question. If the pressure becomes 4 times, what happens to the velocity of sound? That's the question. If P increases, what happens to speed of sound? This was I think question 80 or something. Pressure became 4 times, what happens to speed of sound? Most people will think, okay, P became 4 times, the root will come out, the velocity is double. You have to be careful. If P increases, then volume decreases. If the volume decreases, then density increases. right? And it increases. So at a given temperature, if you look at the formula, P by rho is nothing but R by T by molecular weight. This remains constant. Means if you increase the pressure, density also will increase. So P will increase, rho will increase, and P by rho will become constant. So be careful. Speed of sound is independent of pressure. It might give you an illusion it is depending on pressure, but it doesn't. It depends only on the temperature and molecular weight and the type of gas. Speed of sound is independent of pressure and depends only on temperature. Yeah. Second thing, what happens with humidity? If you increase the humidity in the air, meaning you can see monsoons, right? Now the water is more, there is more humidity in the air, or during winters there is more fog in the air. Fog is kind of a humidity. With increase in humidity, so humidity is nothing but you're replacing air molecules with water molecules. What is the molecular weight of air molecules? Roughly around 28. Most of it is nitrogen. And what is the molecular weight of a water molecule? 18. So M is actually decreasing. The speed of sound increases. That means sound travels faster in a foggy night than a normal time. You can think of an extreme case. There is so much water in the air, everything becomes liquid and sound travels faster in liquids. Clear with this? That is a little bit of a theoretical questions. Let's see a question on this. There. So till now we got a bunch of formulas there. Let's see a question on speed of sound. So this formula you should know. Gamma RT by M. Let's say we have a region where this is x is equal to 0 and this is x is equal to 100 meters. This whole space is filled with a helium gas. Temperature here is 100 Kelvin and temperature here is 300 Kelvin. And temperature is increasing linearly. And in this region, you're sending a sound wave. Temperature varies linearly from x is equal to 0 to x is equal to 100 meters. From 100 Kelvin to 300 Kelvin. Find the time taken for the sound to go from one side to the other side. If I give you a constant temperature, that was easy, right? So this is a variable temperature. Let's say how will you do this? Yeah, there's the only formula you have, gamma RT by M. So let's see how will you use this. Give it a try. Yeah, numbers are a little bad, but let's see if you got the equation. I'll give you a minute more. Get the main equation. If you got that, you're done. First thing, he said temperature is varying linearly. Let's start from there. The function is changing linearly. How does it look? It looks like y is equal to mx plus c. So t is equal to ax plus b. That's a linear function. So at x is equal to 0, your temperature is how much? 100. This will be equal to a into 0 plus b. So b is equal to 100. At x is equal to 100, temperature was 300 Kelvin. That was a into 100 plus b. But b is already 100, so we'll get a is equal to 2. There we got the function. So temperature is 2 into x plus 100. That's your function, everyone. So this is the temperature changing with x coordinate. Now the speed of sound is given by root over gamma RT by molecular weight. This can be written as, and gamma ka value I know. Gamma is nothing but 1 plus 2 by F. F is helium. So that is 3, 5 by 3. Molecular weight ka value I also know, which is 4 into 10 power minus 3 kg per this thing. So I can write this thing, V sound is equal to root over 2 times gamma R by M into x plus 50. Yeah, at this point, you can just directly write dx by dt, integrate and do it. That's one way to do. So I can write this thing as dx by dt and do the integration. There's a better way. Square it on both the sides. I get v square is equal to 2 gamma r by m x plus 100 gamma r by m. This guy is looking like v square is equal to 2as plus u square. Can you see? It looks like the kinematics third equation, where you can clearly see u is the initial speed, 100 gamma r by m. The sound wave is actually traveling with a constant acceleration. Acceleration is gamma r by m. So the sound wave thinks it is accelerating. I hope you can see it. It gives you the vibes of, that question. The string is hanging from the ceiling. It had a constant acceleration. Once I know this, then I can use the equation S is equal to ut plus half at square and done. I know the values here. S is nothing but 100 meters. U ka value I know, A ka value I know. I'll get a quadratic. You solve this, take the positive root. We can leave it there. Samyak did get something. Root 1000 by root 3 minus 1. Yeah, it's a big number. Then you can convert it into a kinematics problem and finish it off. All clear with this? So first thing is finding the temperature as a linear function. Once you got that, we can use V sound and we can get this. Do have a look at the steps. But that's a bit about speed of sound. So the questions are straightforward on this. The next thing is intensity of sound. Again, there's nothing new to do here. If you remember the formula for intensity we derived there, the formulas are exactly the same. So intensity is given by half rho a square omega square v wave. What is v wave here? In a longitudinal way, v wave is root over b by rho. And what is delta p max? BAK. So they'll give you any two of them and they'll ask you for the third one. So you should know these three formulas. So these are the main ones. Intensity, velocity of the wave, and the delta P max. But this is a very not a convenient way to study, intensity because the values are very small. So we study this in terms of decibels. I'm sure you must have heard this word. So decibels beta is given by, it is a log scale, 10 log intensity by I naught. We will talk about this. Because these values are so small, studying them in terms of intensity doesn't really make sense. So we study in terms of log scale, just like your pH scale, 10 power minus 2 watt per meter square. So we study in terms of decibels. This is the formula there. We'll discuss this after the break. So take a break, come back by 9:45. We'll continue from here. Any doubt so far? Chalo, come back by 9:45. Comes on everyone. So what are these decibels? You see, right, when these numbers are so large or so small, studying them directly, right, kind of doesn't make sense. So we put a log scale. For example, say your simple pH scale. If you see your pH scale, how it is defined, it is simply log H plus concentration. Now, if you try to study H plus concentration directly, look at what happens. If you say this is 10 power minus 1, which is 0.1. On this graph, where will you write 10 power minus 2? 10 power minus 2 should be 1/10 of this. So this will be 10 power minus 2. Where will you write 10 power minus 3? That will be 1/10 of this. So that will be somewhere here 10 power minus 3. Where will you write 10 power minus 4? You can't draw it anymore on a graph. It becomes very difficult. So by putting it in a log scale, you're making it little easy. So when someone says an acid of pH 3 and pH 6, you know how strong is the pH 3 acid compared to pH 6? It's not double, it's 1,000 times. This is 10 power 3 and 10 power minus 6. So in a log scale, every one number, right, goes into 10 times. Similarly, when you look at earthquakes, ever heard about this thing, Richter scale? They say today there's an earthquake of 6.7, 7.2. This is actually something like 50 log the energy released in an earthquake by E naught. This is the Richter scale value, something like this. So when someone says there's an earthquake 6 and an earthquake 7, the earthquake 7 is 50 times more stronger than earthquake 6. And when someone says Richter scale is 8, that means it is 2,500 times more stronger than 6. So every 1 unit of that bumps up by 50 times more energy. So all these are log scales. So in decibels, right, it is 10 log I by I naught. So the I is the intensity of the sound, I naught is a reference value. So these values can be very deceiving. For example, if intensity doubles, the change in decibels, if I try to look at the value here, see this thing, beta nu will be 10 log 2 times I by I naught. This can be written as 10 log 2 plus 10 log I by I naught. So the new decibels minus the old decibels is 10 log 2. Log 2 is roughly 0.3, so this thing comes out around 3 decibels. So whenever the intensity doubles, you actually change only 3 decibels. So when someone tells you, right, the intensity of sound has gone from 50 to 59 decibels, you might think like, oh, only 9 decibels. No, it is not 9. 50 to 53 doubled, 53 to 56 doubled, 57 to 50 doubled. So if this is I, this is 8I. The sound has become 8 times more intense. So these decibels can be pretty deceiving. Like it's close to 3 decibels. Suppose if intensity becomes 10 times, change in decibels is 10 decibels. So beta nu will be 10 log 10 I by I naught, 10 log 10 plus 10 log I by I naught. So beta nu minus beta old is 10 decibels. So for every 10 decibels, intensity becomes 10 times. So I can ask a question like this. Let's say the intensity goes from 50 decibels to 100 decibels. If 50 decibels ka intensity is I, what is the intensity of 100 decibels? At intensity I, we get 50 decibels. Then to get 100 decibels, what should be the intensity? People will think, oh, 50, 100, so double over. It's not double. For every 10 decibels, you became into 10 times. So 50 to 60, 10 times. 60 to 70, 10 times of 10 times. So this would be 10 power 5 I. 1 lakh times more intense sound. Is that making sense, everyone? So when you go from 50 to 100, the sound has actually become 1 lakh times more intense. That way. Can you have negative decibels? You can have negative decibels. If your intensity is less than minus 10 power minus 20, you can even have negative decibels. So it is simply, it is just a reference scale there. But generally, right, when the room is very calm and silent and all, even then in your room, you might get around 30 to 40 decibels. But if you make the room really quiet, uh, there is the world's quietest room. You get minus 24 decibels there. This is called an anechoic chamber. Have it in a few universities, and it is also used as for the sound capturing and all that stuff. Let me show you how it looks. Here is the slide. Yeah.
Keep going to slow my breath down.
Great.
Ready?
Yeah.
Okay.
Now, look at that. When she's shouting. If you look at the room, right? The entire room is made of just wedges and everything. So whenever the sound goes into the wedge, it gets absorbed, or it just keeps getting reflected between the wedges, and eventually it gets absorbed. So in this room, right, there is never a reflection. Means if you shout in this room, you'll never get a sound back. Now, when this lady is shouting, see, observe what happens. When she's shouting towards the camera, sound is high. When she's turning her head towards the wedges, the sound decreases. So let's hear that again carefully.
Ready?
Yeah.
Okay.
Can you see the difference in intensity? So whenever she's towards the walls, the sound is getting absorbed. So you're not getting any sound. I posted in the group. You can listen more clearly.
That was outstanding. Thank you. The quietest place on earth is apparently an anechoic chamber in Minneapolis. Now, I'm here at BYU at their anechoic chamber. Anechoic is Latin and basically means no echo. And the way they achieve no echo is through all of these foam wedges, which are put on the walls and even the floor. You can see that I'm actually
Look at the floor, actually. Floor is also made of a metal cage, and even those wedges are at the bottom. So this whole room is covered with these wedges. So there's no reflection. If sound doesn't come back, it goes and gets absorbed, kind of like a black body, where the wavelengths get absorbed. Here the sound is getting absorbed.
Spring floor, and down below me there are all of these wedges. Now, you may want to use headphones while you're listening to this video because that's going to be quite important. Low frequency sound will come in and by the shape of it bounce and just keep bouncing pretty much forever until it just gets lost in the wall. And then high frequencies are more so going to get absorbed in echoes by clapping constantly.
I'll send this thing, so do make sure to check it out. It's a good video. So that's called an anechoic chamber. So they're one of the quietest rooms in the world. I think very few universities have it like. So in that room, right, if you make you sit in that room and close the door, the room is so quiet, you can start hearing the blood flowing in your brain also. You can hear everything that is happening in your body, the blood flowing in your hands, blood flowing in your ears. Did you ever do this thing? You take your hand like this, make like a cup and put it on your ear. Make your hand like a cup and put it on your ear. You will hear a sound like, shh, kind of thing you'll hear. Observe that carefully. Your room has to be quiet. Can anyone hear that? There is a very faint shh kind of sound. Maybe not now, try later on, but keep the room whole thing quiet and just put this thing. Or did you ever hear this? If you take a Sika shell and put it near the ear, you can hear sound waves of the water waves. Ever heard that bullshit? Getting it? That's a nonsense thing. Getting it? So what you're actually hearing is, what? When you keep your thing like this near your ear, you're hearing the blood flowing in your hands. You're hearing the blood flowing in your ears. That sound which you're hearing is actually the blood flowing in your ears and your hand. In day-to-day life, there is so much, background sound. These things get mixed up. But if you make your room very quiet, you can hear your everything in your body that is moving. You can literally hear your blood flowing in your body. Why all that? Tell me one thing. In winter, when it is very cold, why do you switch on the fan and sleep? Why do you switch on the fan? Is it because you want the wind? No, you want this background sound, isn't it? That fan will create a kind of a background sound. It's called white noise. And in that sound, right, all other sounds will get mixed up. Try to do that. If you don't have a habit, right, try to switch off the fan, make your room really quiet and try to sleep. You will hear every damn sound. The clock are ticking, tick, tick, tick. Somewhere small noise, somewhere some insect is doing small sound. It starts irritating you. You can start observing everything. Then you switch on the fan. So the fan will create a background noise and all other sounds get absorbed into that. So it feels like it is normal. So if you see, most people have a habit of switching on the fan and sleeping, not because they want that breeze or something. They actually want a background sound. So that's a thing there. So let's see a question on this. Let's say we have a point source. So in a point source, the sound is traveling in spheres. When you're speaking, you're a point source. The sound travels in spherical wave fronts, basically. So let's say this is point A and this is point B. So the distance A from center is capital R. Distance of B from center is 2R. The second one, we got a line source, meaning the sound, right? It is like a vertical speaker or something. For a line source, the sound waves are coming like cylindrical wave fronts. So the sound is coming like a cylinder. You can think of equipotential surface. They kind of look like that. Same thing. So we have 2 points here, A and B. RA, RB, same distance. Find the difference in decibels between A and B. What is the difference in decibels between A and B? Let's give it a try. Where is the world's loudest room? See, the thing is, once you reach around 120 decibels, your eardrums will burst. At that point, you become anyway gone, right? 120 decibels, that kind of sound is generally, I think the loudest sound that we have is something like this, which we can capable. When you launch a space shuttle, right? During that time, you get really these kind of sounds. If you can hit 180 decibels, the universe will explode. So that 180, right, might look like a small number, but remember everything it is having 10 power more, 10 power 10, 10 power 12, 10 power 13. So you can 180 decibels, the universe fabric will break down, and yeah, the black holes also will start vanishing off. Those are all theoretical numbers, but I think practically we can create up to 120, I guess. That's a huge number actually. Yeah, let's get this. Yeah, Param, right. Right, Samyak. Everyone should give it a try. Let's see. First of all, what is intensity ka formula? Intensity is power by the area in which it transmits. So basically, it is like how the energy is getting spread out. So for the first case, it's going in a spherical wavefront. So power will be P by 4 pi r square. So intensity is proportional to 1 by r square. So intensity of A by intensity of B will be 2r whole square by r square. So that is 4:1. And we know for every time the intensity doubles, you get 3 decibels. So that will be approximately 6 decibels. So for every 3 decibels, intensity doubles. The second one, you are going in a cylinder, so the surface area is 2 pi RL. So I is proportional to 1 by R. That's the difference. Now IA by IB will be 2:1. So in this case, the difference in decibels is 3. There, that's the difference between a point source and a line source. In a point source, the area is 4 pi r square. Yeah, I mean, you can, the exact value will be 10 log 2. This exact value will be 20 log 2. That's the exact value. We approximated it. Clear with this? That's a bit about intensity in terms of decibels. So that is one important thing. The next thing. Again, the important part, stationary waves. So we saw stationary waves on a string. We will see stationary waves in a sound waves. The theory will look kind of mostly same, except one or few things you need to learn. So let's see that. Stationary waves in sound. For a stationary waves in a string, we used something called sonometer. Here we are going to use something called organ pipes. That is the name of them, but organ pipes are simply, these are thin hollow pipes. So first, let's study how these pipes behave, and then we'll go ahead. So there are two types of pipes we have. Open, meaning both the sides we have an open end. The second one is an open closed. First, let's talk about open. So in an open pipe, both the sides of the pipe is open. So simply a hollow pipe. This is an open end. This is an open end. Now listen carefully here. Since the open end is exposed to atmosphere, the pressure will never change. Because the open end is placed in the pressure, right? It is exposed to atmosphere. So the pressure cannot change there because you have to change the whole atmosphere then. Therefore, pressure remains constant. Now, in a stationary wave, if something is not changing, it is called a node. So these open ends are actually pressure nodes. Understand the meaning of nodes. The property is not changing. So at an open end, we get a pressure node. Similarly, the particles at the open end are not attached to anyone. They're free to move. Because they're not restricted, they can move however they want. This is like a free end. So this is a displacement antinode. So you have to be really careful. If someone asks you what is an open end, the first question is, are you talking about pressure or displacement? So an open end is a pressure node or a displacement antinode. Both are right. So the question comes, do you want to study in pressure or you want to study in displacement? So if you look at this, this gives you a feeling of a sonometer like this. If you take a sonometer, this was a node, this was a node. So mathematically, if you see, they kind of look the same. This is the important part, everyone. Is this making sense? At an open end, the pressure cannot change because you're exposed to atmosphere. So it's a pressure node. At the open end, the particles are not fixed. That means they can freely move however they want. That's a displacement antinode. So both are right. It's a pressure node and a displacement antinode at the same time. So the question comes, how you want to study? You want to study in terms of pressure or displacement? Any doubts on this page? This is the main thing. Once you got this, the rest will start looking identical. So how do you generate standing waves inside this? Just to give an idea, what is an organ pipe? Flute is an organ pipe. One of the best example. Like I said, every musical instrument is based on stationary waves. All stringed instruments like guitar, violin, all these things are sonometers. Flute, tabla, right? Drums, all these things are organ pipes. Tabla is a closed and a closed pipe. Flute is open, open. You're getting it? So every musical instrument you can think of, either it is a sonometer or an organ pipe. So in a flute, what you do by closing that holes, you're creating different lengths. So this is what we do. We keep a tuning fork of frequency f. So this tuning fork will send a wave, an incident wave. It's a node, so it gets reflected there. It's like a fixed end. And the sound bounces off there and you get a reflected wave. So the incident waves get reflected at the open end. Now you might think like this, sir, won't the sound just leak out? See, sound is not some kind of a water flowing in a pipe. It won't leak out. This is what is actually happening. When a compression comes here, remember compression is a high pressure region. So when it comes to the open end, because there's a high pressure here and a low pressure here, the gas will leak out. When it leaks out, it won't stop at P naught. It will continue to leak out till you get a P naught minus delta P. You go to the other extreme. So when a compression comes, it will leak out the gas and you'll become a rarefaction. Suppose if a rarefaction comes here, you're getting a low pressure region. Atmosphere will push the air inside and you will reflect a compression. So if a compression comes to an open end, it becomes a rarefaction. Rarefaction becomes a compression. So you should think of it like that instead of thinking like a sound, some like a water which is leaking out. It's like bouncing off. The atmosphere will push or will absorb that high pressure thing. The incident and the reflected waves will overlap. Remember, in a stationary wave, we need two waves going in the opposite direction. Superpose to form stationary waves. So if you write the equation, we get delta P incident. We'll get delta P max sine kx minus omega t. Delta P reflected will be delta P max sine kx plus omega t. When you add them, delta P resultant. This looks like sine A plus B. We end up with 2 delta P max sine kx cos omega t. I hope you can see the resemblance. This guy is looking like y is equal to 2a sine kx cos omega t. Only difference y का place में we got pressure. So we define something called pressure amplitude. Which is 2 delta P max sine kx. So wherever there is y, that became delta P. Wherever there is a, that became delta P max. Mathematically, they look exactly the same. Max does not know the difference between y and delta P. All clear with this? I'll show you how this looks. Now, what is the first possibility? Again, the same story. Remember, the only condition you have to satisfy, this is a pressure node, this is a pressure node. I'll show you both displacement and pressure. First possibility. Let the length of the pipe be L. This is a pressure node. Remember, we will study in terms of pressure, but yeah, I'll show you displacement also once. Pressure node. So the only condition you need to satisfy, both of them should be nodes. Means you get one loop. Same thing, a sonometer ka story only. But here we are studying pressure. Or if you want to study displacement antinodes, so this will be displacement antinode. This is a displacement antinode. Both are right, but like I said, we prefer this. So the wave will look like this, an half wave and an half wave. This is how the graph will look like. End of the day, the length of one loop is lambda by 2. So we get lambda by 2 is equal to L. So we get wavelength is equal to 2L. So we get frequency is equal to V by 2L. Can you see the formula is exactly the same? This is your first harmonic or fundamental frequency. The second possibility. We get two loops. Again, I'm using pressure. So this will be 2 times lambda by 2 is equal to L. So we get the frequency F2 will be 2 times V by 2L or 2F1. This is your second harmonic or first overtone. The whole story is same. So the general formula will be Fn is equal to Nv by 2L. The only difference here is V will be root over gamma RT by M, speed of sound. That is the only difference. Other than that, the whole thing will look the same. N is the number of harmonics. In a sonometer, V was root over T by mu. Here it is gamma RT by M. So if you generate frequencies in this is the sound you get. So the shape which I'm drawing, right? In sonometer, it was clear. Those are positions of string. What am I drawing here exactly? So are you guys can see the resemblance with the stationary wave sonometer? The formulas look same. Right, Kashyap? Now, what am I drawing here? What is the shape of this? Listen to this carefully. I'll show you something on this. That shape which I'm drawing here is actually a graph. This was your x-axis. This is your delta P. So this is a graph between pressure versus X graph. So when you're drawing it like this, you're telling at the nodes, there is no change in pressure. Change in pressure. Huh? At the antinodes, the pressure is 2 delta P max. That means in the cylinder at different points, you have different pressures. At this point, the pressure will be 2 delta P max sine kx. So this shape which you're seeing is actually the pressure at every point in the cylinder. That is the meaning of this graph. But problem, what? We can't see this directly, right? So then how do we see this stationary wave inside? We have few tricks there. Listen to the thing. I'll show you this experiment. So what these people do, they take this cylinder, they fill this inside with propane gas, which is flammable. And then what we do, we make holes every 1 centimeter, we make a lot of holes. Now look at the story here. Outside the pressure is P naught, and node mein pressure is also P naught. Delta P is 0. So gas will not come out at nodes. At the center antinode, the pressure is 2 delta P max extra. So here the gas will come out with more force. Here the gas will come out with less force, less force, less force, less force. This is how the gas will be coming out. Now, if you put a fire, you will see a flame like this. Is that logic making sense? If I fill the cylinder with propane gas and if I make holes, wherever there is more pressure, gas will come out faster. Now, if I put a fire there, I should see a bigger flame there. That way, I can see the stationary waves. So what you're seeing is the fire. So from there, you can see the pressure. So there is an experiment like that. It's called Rubens tube. Normally, we don't do it in the labs because we don't trust the students. But yeah, this is how we do it.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of the 2-inch tube. On that side, we've got some black leading to some pro.
So there, so Piche, he has a PVC pipe. On the left side, he kept a speaker. Right side, he connected it to a propane gas cylinder. So the gas is getting into the pipe. And this whole pipe has around 100 holes. Every half-inch, he made a hole.
Okay, so let's fire it up and see.
Now, if you just switch on the flame, speaker is off. There you get a flame. You can see they all are same height. So there is no sound inside, nothing. So they're almost coming out at the same height.
As you can see, we have some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there, see what happens.
Now, if you change the frequency, can you see that? When you get 449, you can see at some points, yeah, these are not perfectly right, but some points the flame is bumping up, some points the flame is gone down. So you can clearly see there's a 4 loops. Those are 4th harmonic.
As you can see, this sets up time there is they're having the sound from here. A little bit pressure here, a little more gas escaping the atmosphere, shaping the sound curve. Now, if we change the frequency,
See, the 6th harmonic. You can see every frequency won't give a harmonic. Only specific values will give you a stationary wave.
the
6th harmonic. Then you can clearly see 6 loops.
If we get that sound curve, higher the frequency, the more wave. Now let's put some music in. Let's put some Dave Brubeck.
Now, if you put some music, then yeah, fire actually, reacts to the sound.
Now we have real sound. Fine.
Yeah, so that's called a Rubens tube. So this is another one. The video is more clarity. So if you put a music there, you can literally see the dance, the fire is dancing to the sound. You can make this even better. You can make a two-dimensional Rubens tube. There.
Go for it.
So this thing, see, they made a big table. So this thing, there's a gas burner kind of thing. So this is like a big square plate with holes equidistant. Now you're sending the sound in x-axis and y-axis, both the directions. You can have stationary waves in two-dimensional. So this is the Rubens tube in 2D. Now when you play the music, look at the fire.
Now, you may have seen a Rubens tube, but you pump in a flat rhythm sounds into the tube, and you can actually set up standing waves. That is, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now, that affects the flow rate of the gas inside that tube into the atmosphere. You can in Denmark with but this.
So look at the flame, how it goes. It looks like some graphics. That's actually a flame. So you can play music. After that, you can cook some food also. Multi-purpose. So that's how a Rubens tube works. So that is how you can actually see a sound wave, a stationary wave. And now all clear with this thing? What is the meaning of this graph and the cylinder and everything? Hope that is making sense. Now, if you take an open closed pipe, we'll finish off the theory part today. Next class we'll do all problems, but there, I hope you can see now, this thing looks exactly like the sonometer thing. So in an open closed pipe, the one side is open, one side is closed. So we already saw this is a pressure node. The open is a pressure node. And a displacement antinode. Now this point here is fixed. The particle at the closed end is fixed. It cannot move. So this is a displacement node. So the particles at that fixed end cannot move. This is a displacement antinode. And this is a pressure antinode. So particles at the fixed end, at the closed end are fixed. You know, what is this looking like? This is looking like the free end wala problem, if you remember. This was a node and this was an antinode. So this one, open closed, is exactly this question, a free end wala problem. So this is what I said. What have you learned in stationary waves on a string? The logic, everything works same. Only difference, the pressure becomes displacement and everything. So what is the first possibility here? So the formulas also look same. So the first possibility, this has to be a node and this has to be an antinode. You get an half loop. This is length L. Lambda by 4 is equal to L. So we get the frequency F1, which is V by 4L. Should go and check it out. You got the exact same formula there. And this is your first harmonic or fundamental frequency. The second possibility, we will get 1.5 loops. So we get frequency F3 will be 3 times V by 4L. We get 3F1. Third harmonic or first overtone, even harmonics are missing. Nothing changed, except you called it sound and waves on a string. Mathematically, you can't tell the difference. This is your first overtone. So the general formula will be Fn, which is 2n plus 1 B by 4L. Right, where n is equal to 0, 1, 2, 3 are overtones. And even harmonics are missing. There. So the main idea is to realize an open end is like a node for a pressure node, and the fixed end is a pressure antinode. As long as you remember that, you can always compare it with a sonometer and you can finish it off. It becomes straightforward with that. Hope you can see the resemblances. In this, there is one more small thing called an end correction. But the problem is when the wave comes and hits the open end, it immediately does not reverse. Because of inertia, it pushes the node slightly outside. And open ends, the pressure node forms slightly outside. So that means for an open end, the nodes are forming slightly outside. So the loop is actually like this. This distance is called end correction. This would be L. This would be E. So that means lambda by 2 is not L, it is actually L plus 2E. And the frequency ka formula, so nothing much. The frequency ka formula is N V by 2L. Wherever there is L, replace that with L plus 2E. The formula changes like this. And what is the value of E? E end correction is given by 0.6 times the radius of the organ pipe. Or 0.3 times the diameter. So they will give you the radius or the diameter in order to find the end correction. If it is an open and a closed end, there's only one open end. There's only one end correction. So wherever there is L, it will become L plus C. So the formula will be 2n plus 1 B by 4 L plus C. There. So just keep that in mind. That's an end correction. So the node forms slightly outside. All clear with this? That's the theory of the sonometer. Now in this, we have two experiments called a resonance column tube and a Kunz tube. So we have two experiments and everything is based on, these formulas only. We primarily only have like what? This formula, pressure is 2 delta P max sine kx. And then this formula, NV by 2L, and this formula, 2n plus 1 V by 4L. The questions will look quite identical to what we did in sonometer. End correction is because when we said, right, when a wave is coming and hitting the open end, it suddenly cannot reverse. It will push the atmosphere slightly outside and then it will bounce back. It's like if you're going and hitting a very strong guy, no matter how strong is the other person, you will move them a little. Clear with this? So that is the theory of this thing. If you see today, we had a lot of theory there. The chapter is like that. If you see, but if you know your main formulas and everything, you can actually handle most of the questions. Hope everyone has started doing waves on a string, right? So do try to finish it off by next week maximum, because sound waves won't take much time. I think we'll finish off this in another 1.5, 2 classes max. Next class we will do all problems on this. Then we are going to do something called beats, and then I think we'll also do a little introduction on Doppler effect. So next week that we will wrap up this chapter. So do start solving. And we have done almost 30 questions. So do go through the notes. There is a lot of theory and a lot of things to remember. Okay, with that we'll wrap up for the day. I'll see you guys again on Tuesday, same time. So, and there is an exam tomorrow. Make sure to give. So